All right, hello and welcome this evening to our event, Is There a Reproducibility Problem in Climate Science? I'm Alan Love. I'm the director of the Minnesota Center for Philosophy of Science and will be your host for the evening. Before I dive into our topic for tonight, I wanted to give a brief overview of where this event comes from. It comes out of a larger project that is sponsored by the College of Liberal Arts at University of Minnesota that is about questions of reproducibility across the sciences and includes questions about how that science intersects with public trust and research that has an impact on economic and public policy. So that's part of the reason why we call them Conversations about Science and Society. As you might have noticed when you came in, we are video recording this evening, so we will be able to share the evening with others afterwards. And also, when you came in, you might have gotten an index card, but we will do questions and answers at the end. Those can either be by handing the index cards into to myself, or I can bring the mic to you. So that'll be towards the end, and I'll make an announcement about that when we get there. So let's turn to our topic for tonight. Studying climate processes and their history helps scientists understand how and why changes occur in the Earth's climate. Conclusions that converge on similar answers despite incomplete data can increase confidence in the accuracy and predictions derived from climate models. Achieving this kind of reproducibility, which increases the credibility of future projections made with these models, raises some key questions. However, these questions are not those you might typically expect in the context of climate change. Some organizations have tried to wield questions about replicability as political weapons, with the aim of undermining policies directed at mitigating climate change, such as environmental regulations. For example, legislation was introduced as far back as 2015 in an attempt to block the Environmental Protection Agency from using research that is not substantially reproducible. If you came tonight expecting us to engage these political controversies, I'm here to warn you that is not our focus. Instead, we think there are several things that are more interesting and important to discuss. It all starts with something that the political controversies overlook. What counts as substantially reproducible is not so simple to determine. The fact that reproducibility has been a concern with respect to the methods in and results of a variety of sciences, from cancer biology to social psychology, masks that the causes for concern, if there are any, turn out to be complicated. And often they only make sense in the context of specific research programs or disciplinary approaches. That's what spurred our project and its name, The Many Faces of Reproducibility. So what kind of key questions do we have in view for tonight's conversation? The questions we have in mind are similar to those broached in a 2018 National Academy of Sciences report entitled Perspectives on Reproducibility and Replication of Results in Climate Science, where they recognize that, quote, the terms reproducibility and replicability are defined and used differently across the climate science disciplines, end quote. Because of this, it is necessary to get into the details of how climate scientists go about their everyday work and ensure that their analyses and findings can be used by other members of the scientific community, both now and into the future. How can climate scientists develop data formats and produce open source software that facilitate transparent workflows in the face of sparse resources? To what extent are climate model projections reproducible by other groups? How can physical specimens that are often unique, like sediment cores, be archived sustainably? And will science agencies prioritize preserving irreplaceable collections to facilitate replicability? Our panelists are two scientists who have been working on topics in climate science for quite some time. In fact, one of them was involved in helping to write that 2018 National Academies of Sciences report. Let me introduce them to you. On my far left is Gavin A. Schmidt, director of the NASA Goddard Institute for Space Studies in New York. He's worked on understanding past, present, and future climate change, mostly through the development and evaluation of Earth system models. He's been the director of GISS since 2014, and in 2021 served as the acting senior advisor on climate science to the NASA administrator. He was the author in 2009 with Joshua Wolf of Climate Change, Picturing the Science. And in 2011, he was the inaugural recipient of the American Geophysical Union Climate Communication Prize. His 2014 TED Talk on climate models has been viewed more than 1 million times. His effort in communication have often revolved around trust in the process, in the data, in the science and in the scientists, and reproducibility and all its senses have been central to these efforts. Nearer to me on the left is Scott St. George, Head of Weather and Climate Research at WTW, a global insurance advisory firm based in London. Previously, he was Associate Professor of Geography at the University of Minnesota and a research scientist at the Geological Survey of Canada. In his research, he used tree rings and other natural weather archives to extend our perspective on recent climate change farther into the past and understand the risks of unusual or extreme environmental perils. He holds a doctorate in geosciences from the University of Arizona and is a fellow of the Alexander von Humboldt Foundation in Germany. He lives with his family in the Longfellow neighborhood here in Minneapolis, or at least in town, since we're in St. Paul. Although most of us have heard climate science mentioned frequently and perhaps even discussed in detail, I think the best way to start tonight and our conversation would be to review some of those basics, both in terms of key areas of research, perhaps some of which we don't typically think of, and of what we know or what we don't. So I'm going to turn to Scott first and ask for you to help start us off on some of those basics.
Well, thank you, Alan. And hi, everyone. It's very nice to spend the evening with you talking about climate science and the unique challenges we have in trying to reproduce what we know about how Earth's climate is changing. I guess the first thing I would say is that the signs of change are all around us. I don't know, does anyone know what the high temperature today was?
88? Really?
Oh my goodness.
It's 88 and the trees don't have leaves, and it's in Minneapolis and St. Paul in April. That's unusual, but not out of line with the way that we've seen changes over the last 20, 30, 40 years. We don't get as many sub-zero days here in Minneapolis as we used to in the 70s and 80s. That's something that's maybe hard to notice, but when you look at weather experts, if you go talk to the people in St. Paul who are responsible for keeping the long-term weather records for Minnesota, they can tell you the winters aren't as cold as they used to be. If you look a little further west and you think about what's happened in places like California and Arizona, even though California has been hit by some big winter storms that's loaded up the mountains with snow, there's still signs of a very severe extended drought that's really been happening since the turn of the millennium. And so we see all these signs around us that the world that we live in today is not the same as it was when I was a kid or when my parents were growing up. And it's no mystery why that's happening. It's happening because of us and the collective influence that all of us have had on the way that the Earth behaves and the way the climate system behaves. And so if we want to understand what's in store for us in the future, climate science gives us a way to understand not only what has happened, but why it's happened. And the main reason why we're seeing these changes is because of us.
Gavin, you want to?
Yeah. Do you want to just make that go? Can we do
See
that?
if I can.
So as Alan mentioned, I work mostly on climate models, and their attempts to encapsulate all the things that we think of as being important for the climate system. We encapsulate those in simulations like the one that you're seeing above me, with the idea that if we have this digital twin, we can kick it and we can see how it reacts, and therefore hopefully get a sense of how the real world will react. What you're seeing here is very colourful. Obviously, it's not real, right? It's a simulation. All the different colours are particles in the atmosphere. So the orange ones are dust from the desert areas. The green ones are organic carbon from the forests and the land plants. Red are fires that are putting out a lot of pollutants into the atmosphere. The blue in the ocean is the sea salt, and you can see that gets very high when there are big tropical cyclones. You can see the weather systems around the south. You can see an awful lot of complexity. And there is an awful lot of complexity, but the real world is even more complex. And so each of those things that you're seeing there, they are having an effect on the climate because they're interfacing with radiation coming from the sun or radiation coming from the earth or clouds. But you can see that they're being affected by the weather and the climate as well, right? So there's this very complicated interface, interaction, dance between all of the elements that are important. And trying to understand and trying to pull out kind of simple numbers or simple attributions out of that can be daunting. But the interesting thing is, like you mentioned just now, it's, oh, well, we know it's us. Well, how do we know that, right? That's a very interesting question, and one of those questions that really touches on your introduction, which is like, well, how should we normal people have trust in those kinds of statements, right? Where does that come from? How robust are these things? Is it one thing that somebody just kind of wrote on the back of an envelope, or has it been reproduced again and again and again with different systems, with different attitudes, with different forcings? And it's the latter, right? So when we try and work out why things have happened, we have a whole list of things that could be changing the climate. You can see some of them here. There was a volcano a little bit earlier on that you might have seen. But changes in deforestation, changes in air pollution, all of these things will affect the climate. But what precise fingerprint will they have on the climate? That's where these models come into it. We have lots of different models that have different heritage, different coders, different assumptions, and yet they all give us the same answer. They all say that none of those things are important for the trends that have been seen over the last 50 years. It's almost all because of the increases in greenhouse gases, and chief among those is the rise in carbon dioxide. And there's some very specific spatial, vertical fingerprints that come with greenhouse gases that don't happen when it's the sun that's causing it, or if it's volcanoes that are causing it, or if it's deforestation. There's some very, very special things that happen. And those fingerprints have had to have been reproduced, not just with one model, right? In the 1980s, there was one model that did this. And everyone said, well, that's not good enough, right? We're not sure. And so other models came in. And then other models, and then new models, and then higher models with more details and more representation. And they all continue to give the same answer, kind of like demonstrating very much in real time how the trust in that conclusion has been a function of the reproducibility of the techniques in totally independent ways.
So that nicely brings up reproducibility, because we've now got some of the basics on the table. So maybe, Gavin, you were one of the authors of the 2018 NAS report that I mentioned before. Maybe you can lead us into some of the big questions, maybe starting with paleoclimate data collection and archiving.
Right. So we have data. You mentioned the weather offices in St. Paul that have been collecting instrumental data since the 19th century. But we want a bigger context, right? We know the Earth has been around for 4.5 billion years. Like, we need a bigger context to really understand what's going on. And so we have to turn to the proxy record, the paleoclimate record, that tells us something about the climate, but that is somewhat harder to interpret sometimes. There's a display outside about glacial erratics, right? So big rocks that have been moved a long, long way from where they started. That was actually one of the first clues that there had been periodic ice ages on Earth, instead of everything always having been exactly the same as it was. Right? That goes back to Louis Agassiz and the 19th century discussions on the fixity of the continents and catastrophism in geology. But we have better targets now. We've drilled cores in the ice sheets in Greenland and Antarctica that are, in Richard Alley's famous phrase, a 2-mile long time machine. Whereas you go down, and every year there's a different amount of snow, there's a different quality of snow, there's different chemical traces in the snow that tell us what the temperature was doing, what the accumulation was like, how polluted the air was, and how much carbon dioxide was in the air, how much methane was in the air. And we can look at records from Antarctica, all around Antarctica and Greenland, and compare them. And there have been some great reproducibility issues that have come up, right? So there were 2 projects in Greenland that both drilled cores at about the same time in the 1990s at Summit. One was a European project and one was a US project. And they both drilled down to the bottom. And when they published their results, they were identical. Like everything was changing exactly the same way in both of them until they got close to the bottom. And when they got close to the bottom, they totally diverged. And if we'd only had one of those, we wouldn't have known when it wasn't reliable, right? We would have just assumed that the whole thing was reliable. But because we had 2, right, we were able to reproduce most of what was happening in the first 100,000 years. But after that, you knew that you did not know. And so this notion of reproducibility is very key. The same thing with the records of carbon dioxide in the ice. So that was something that was first thought about in the context of the Greenland ice cores. And there was some records that were published from Cape Century in the early 80s. But then people went to Antarctica and they did it again, and it didn't look the same. And there were more things happening in the Greenland cores that didn't look like what was happening in the Antarctic cores. And they went back to Antarctica, different places in Antarctica, and every place in Antarctica gave you the same record. But every place in Greenland gave you a different record. And what it turned out to be was that there's enough contaminants in the ice in Greenland. There's dust and there's pollen and there's black carbon that it messes with the carbon dioxide. And so you can't use the carbon dioxide from Greenland, but the carbon dioxide record from Antarctica is absolutely solid, and it goes back and has been reproduced down to 800,000 years. And so keep like making sure that we have these reproducible efforts, and that we keep some of the ice, right? So the ice, when it's drilled, is like chopped into like 4 bits. Some of it goes into long-term storage, some of it gets shared by this group, and some of it gets replicated by another group. And we're trying to build in that notion of reproducibility in all the things that they're doing.
So Scott, I know you've worked on paleoclimatology substantially yourself. Would you like to share more perspective on this? And I think maybe you also have a few slides you want to walk us through.
Sure, we can talk about a lot of those details.
Mm-hmm.
So paleoclimatology, like Gavin said, is a way for us to look back further into the past, further than we can look using just the direct measurements that people have made of temperature or rainfall. So if you go over to the state climate office in St. Paul and you talk to them, they have records that go back to the 1880s of people going outside every day, twice a day, to make thermometer measurements of the air temperature, or checking the rain gauges day after day after day after day. It's enormous. It's kind of boring, but it's necessary to build up that long-term picture of how our environment has changed. But that's still just a snapshot compared to the lifespan of the Earth, or the time since the last ice age, whatever kind of long-term perspective that you might be interested in. It's just a century and a half, so it always comes up. The question always comes up. Is what we're dealing with right now really unusual? Can we go back in the past and see things that are different or the same as what we're living through right now? And so we often turn to surrogate measures, proxies, stand-ins that allow us to look back prior to the 19th century and into the last few hundred years, sometimes the last few thousand years, to get a longer-term perspective on what has happened in the climate. Now, this is hard for a lot of reasons. One, it's relatively easy to interpret a thermometer measurement because that's a real physical thing that has a lot of meaning to us and is calibrated. It's something we're very familiar with. But if we're trying to make chemical measurements on the water content of ice, if we're trying to look at the growth of trees, suddenly we're talking about the fingerprint of the environment that's passed through a biological system or a geological system. And so that becomes a lot more difficult to interpret because it's not as simple as a thermometer measurement. It also makes it hard to replicate. And Gavin mentioned the value that we get by going out and looking for the same kind of evidence in similar places so that we can compare two ice core records against each other. And I guess what I would say is that replication is really important, but it's really hard sometimes. And so
Yes.
if we can maybe pull up some pictures. I've got a picture of a tree ring section, and I don't know how far in the future I have to get. There we go. So if we want to build up a long-term record of climate change by looking at either the physical or chemical composition of wood grown by old trees, that's great, but it's really hard in Minneapolis to find a tree that's older than 150 years old because we cut them all down and use them for steamboat fuel or construction or whatever we want. So most of the time when we're looking for long records from trees, we have to go to relatively isolated places in the western mountains, go relatively high up, away from settlements, away from places where people are actively harvesting trees, and pull out records from old trees. There aren't that many of them left on the planet. They're present, but they're present in special places and not in high amounts. Sometimes we can pull logs out of geological situations, places like riverbanks or lake bottoms where trees are preserved for longer periods of time. This is a photo of my colleague Joe Zalesnik, who's a professor at North Dakota State University, and you can see him hauling logs out of the Red River of the North in western Minnesota. This is it's wet and messy, and you come home and your clothes are all muddy, and you fall into the river. It's because it's slippery. It's hard work to pull these things out, and so the records themselves take a lot of effort, and aren't that there aren't that many of them. In the same way, if you're trying to build up a record of past environmental changes or recorded in the sediments at the bottom of the lake, you have to go out on a boat or maybe ice in the middle of winter in Minnesota and jam a core through the ice, through the water, into the bottom of the lake, and then pull it up and bring it back home with you. And then you drop it, and the whole thing sloshes in the wrong direction, and you have to go back and start again. It's tricky to do this sort of thing. You need people that are very skilled technically at retrieving this particular kind of geological information. And then you might be interested in those ice cores that Gavin is talking about. Mm-hmm. But just think about what effort is involved. This is a photograph provided by Peter Neff, who's a professor in soil, water, and climate on the St. Paul campus. And this is a photograph that he shared from an expedition up to one of the mountain glaciers in British Columbia a few years ago. Just think about how much effort is required in hauling all that gear. You can't take helicopters up here usually. You have to haul it up, drill down into the ice, bring it up, meter by meter, keep it in the right order so you don't shuffle anything. And then you have to get it down back to the university here in Minnesota or Ohio or somewhere else without the whole thing melting. It's very tricky to do all these things. And so when Gavin talks about the need for replication in modern records or historical records or proxies, that's a really wonderful goal to have in mind. But it's hard. Field work is difficult. I know people that have died in field work because it's physically isolated and it's hard to do. And so we want to replicate as much as we can, but often the kind of unique records we're looking for are very rare and they're very inaccessible, and they're expensive in people's time and expertise to go out and get and then bring back to the lab or university so that you can analyze them in detail.
So let me. So I totally appreciate how hard this is, but the alternative is to have unreproducible records that nobody really ever knows what to do with, right? And there are a number of ice core records from the tropics where, they were made. They can't be made again because those tropical glaciers have now melted, and nobody really knows how to interpret them. Right? There's one from Tibet that is weird. There's another one from Peru that is weird, and you don't want to diminish the effort that people put in to bring those records down. And like the ones in Peru, they climbed up and they took it down on a hot air balloon. They hauled up a hot air balloon, right, filled it up, and then kind of floated the ice cores back down, and then put them in a refrigerated truck when they got down to the bottom. Absolutely incredible. But if we only have one, nobody knows what to do with it. Nobody knows if it's reliable.
Yeah, this is the perspective of a climate modeler. They always want another record. They always want one more.
So
which is good. It's just it's hard sometimes.
Oh no disrespect to the people. I mean, this is an absolutely heroic type of work. There's no question.
So between the two of you, I've heard both the term reproducibility and replicability. So Gavin, do you distinguish those two things in your thinking?
In my thinking, no, but in my writing, I try to.
Okay.
So I think it's useful to think about a case where somebody's done something and you just want to make sure that they did it right, and so you take the same samples, you take the same methodology, and you just do it again, and hopefully you get exactly the same answer. Right, so that would be what you might call reproducibility. But then replicability, it's like you want something bigger. You want to know that not only did they do the analysis right, but that if they had done it over here or over there or with a slightly different instrument, they still would have got the same scientific results. Right, so you're looking there for scientific replicability as opposed to point-by-point replicability. And in climate models and in computation, there's a very similar notion, right? So if you take a very complicated code and you run it once, you want to know that if you run it again, you're going to get the same answer, right? And that turns out to be a very tricky thing to organize because a lot of these codes, as you saw in that animation, are chaotic. Right, and things when they're chaotic, that means that if something is a little bit different, even right at the beginning, within a month of simulation, it will have totally diverged, right? And that's a feature that we think of the weather, but it's also a feature of these models. And so having a model do something exactly the same as it did previously, right? That's a very high bar for what's called bit-for-bit reproducibility. But most models do that, and that's one of the tests that the modeling groups use to make sure that they haven't put in bugs into the software. But that only works on the same system that they ran it on, with the same compilers, with the same math libraries, with the same options. And if you take it somewhere else, if you run it on a different computer, it won't give you bit-for-bit reproducibility. Right, but what you want is, if it's a climate model, you want it to have the same climate. Right, statistically, it shouldn't be any different from the model that you ran over there. And so that's a little bit less reproducibility, but it's still a reproducibility thing. And then you've got a totally different climate model, and you want to have the same scientific results from that to demonstrate that those scientific results are robust. And that would be a replication by a different independent group using their own methods, using their own model and their own computers.
Okay, so now we've clearly moved into the space of modeling. So paleoclimatology, global climate models. So maybe this is a good point for us to sort of say, okay, what are we talking about? What exactly is a global climate model? What does it mean to worry about their projections potentially not being reproducible? So Scott, can you tell us a little bit about what exactly is a global climate model?
Well, I can give my version of it. So I'm not a climate modeler. Gavin is really a climate modeler. So my version of trying to explain what he does is fairly simple. And so I guess I think of
that's good for us.
A climate model. It's math. It's a set of equations that try to describe how the important parts of the Earth's atmosphere and ocean and biology act and interact together to produce the climate of the world that we live in. So it's mathematical models. Climate models are tools. They're tools that we can use to ask questions about why the climate has changed up to 2023. And we can use the same tools to ask questions about what the climate might do, could do, is likely to do in the future, depending on the choices we make today going forward. Like Gavin was saying, a climate model is a simplification. I think when he puts up animations like the one that he started the session with today, you see all this wonderful turbulent movement within the atmosphere. It looks real, but it's not. It's fake. It's fake. It's the product of one of these mathematical models. It is able to reproduce in wonderful detail some of the real complexity that we see in the world we live in, but it's still not as complex as the real thing.
Right.
And there are a lot of things that are simplified.
Yep.
Or are coarse. It doesn't know the location of every house in the U.S. or across the country. It doesn't even really know where Minneapolis and St. Paul is, because these things are abstracted. It knows where the forests are, but it doesn't know the location of individual trees.
Right.
And I guess the last thing I would say about climate models is the reason why I, as someone who is not a climate modeler, think we should take their predictions seriously is because they have a track record of being right. Gavin mentioned the first models that were made in the 60s and 70s were simple. They couldn't make fancy animations like the one he showed, but they got the details right about the way the world is now, and some nuances too, some subtle things that we only know because the models predicted them, not just reproducing what we saw, but predicted the real changes that we've lived through 20, 30 years in advance. And so for that reason, a lot of people outside the climate modeling community look at the kind of work that Gavin and his colleagues do and think, we need to pay attention to this. We need to take it seriously because it provides us with one way of imagining or anticipating the arc of the world that we live in and how it's likely to behave in the future.
Yeah, that was great. Let me not really add to that, but let me just kind of underline. There's a very famous statistical adage dictum from George Box, and he says all models are wrong, but some are useful. And so all models are wrong, right? As we've said multiple times, like the real world is much more complicated than anything that we can ever create in silico. But their models do turn out to be useful, and we have been able to predict things that we had not observed ahead of time. We made real predictions about things that had not yet happened that using these models that did happen. The most famous one and one that was worthy of a Nobel Prize last year for Suki Manabe was a prediction in 1967 that the stratosphere would cool as carbon dioxide went up and as the lower atmosphere was going to warm. And that was such a radical thing in 1967 that they didn't even mention it in the paper. It's just in one figure. But that was the first prediction of that. And that was before we had even any temperature measurements of the stratosphere. Right? And yet now we've got 40 years of satellite measurements. That's exactly what's happened. And not only is it exactly what's happened, it's like exactly what's happened. And so these models have been skillful. They haven't been perfect. They have been skillful. And by skillful, I mean you know something more than you would have known without them. And so that's the definition. That's the working definition that we use of useful. Right? Are the models telling us something we wouldn't have already guessed from linear extrapolation or something? And they do. And they give us surprising results. So I think in philosophy you sometimes call that a severe test of a model. So it's not the obvious thing that any model would predict, but it's an odd thing that the model predicts that actually ends up being true. And so their credibility has been built on not just reproducing the pretty pictures that I showed, but doing these out-of-sample tests for the future, doing these out-of-sample tests for things in the paleoclimate, right? So there was a big controversy in paleoclimate going back to the 1980s about how cold the ice age really was, and there was some estimates that had come from ocean flora and fauna mainly. That suggested that the tropical Pacific was actually not any colder in the ice age than it is now, and that was a puzzle. the people that produced that result said, no, this is real. This is what the results show, and everyone else says, it's a little bit odd. And it was mediated through climate models where they said, okay, well, if that's the real temperature, then does it match the temperatures that we can infer from changes in snowline or changes in pollen on land? And the answer was no, these two things are incompatible. You couldn't make the model fit both things at once. And so you might say, okay, well, the model wasn't very good. We get another model. But as the models got better and better, you still couldn't make it fit. And it turned out 20 years later that they came back and they said, well, we've done it a different way now. And it was, in fact, much colder in the tropical Pacific, as you might have imagined right from the beginning. But again, those kinds of tests and building a credibility have happened over many decades. And so we're now in the position where when the models say, well, this is what's going to happen if we burn it all, and you end up with a world that is as warm as the Ice Age was cold, and this is what's going to happen even if we stop emitting things now or very soon, and you see those differences. Those are credible predictions, and these are the things that everybody has in mind as we're now trying to roll out climate policies and trying to reduce emissions.
Yeah, I would also jump in to say, I think that success is also hard to work with because it's so different. We are not good at predicting the future. There are no flying cars, there are no hoverboards outside. Generally, we don't think 20, 30, 40 years in advance because so many things happen to make our the best laid plans go awry. And so I think one of the difficult things that we have to wrestle with is that we have these tools that have proven to make credible predictions about the future 20, 30, 40 years ahead of time. And we're not really sure how to handle that because we're not used to making decisions on those time frames. We're not used to having information about the future. And so it becomes harder to use it.
Yeah, kind of, but also not. I mean, do you have a mortgage? How many years does your mortgage last?
Yeah.
Right? Like
Too
my
long.
mortgage is for 30 years. I have a child, and I anticipate that she will hopefully get beyond the age of 37, right? So, we do have some things in our lives where we do think multi-decadally, but obviously there's most of our lives is spent in the day-to-day, which has a very short time horizon. So, but I don't think we're incapable of thinking long term.
So there's a difference between thinking long term and acting for the long term. And so I think this is a good turning point because we've now got some of these basic issues about paleoclimatology, global climate models, what it means for them to be reproducible, why we would rely on them, their track records over time. But then we also have the question of the challenges that face going forward, making sure the ice cores don't melt on us and we can still go back to them later. And so these challenges are going to be financial, institutional, political, societal in different ways. Maybe it would be good to get a little bit of the detail about what is then demanded to address some of those things. So let's stay on global climate models for the moment. Right. I mean, what does it mean for us to make sure that going forward, we're going to be able to build on these past successes and still be able to utilize the data and continue to do these runs?
So it's a great question, and it is a real challenge, right? So the number there's 50 modeling groups around the world, all producing multiple hundreds of terabytes of computer models, simulation data, all the different variables, sometimes very high frequency data, sometimes lower frequency data, and it needs to sit somewhere. And it turns out that nobody really thought about that. They ask us to do all of these things, and then suddenly it's no, open science. All the data has to be available, and you're going, well, my funding was only for 2 years, 3 years. And how long did you want this data to be available? Oh, no, forever. And you go, there's no mechanism for us to invest our research funds into some like perpetual care for dead data, right? I mean, like, one of the things, this is not quite the same thing, but perhaps it's apropos. In the neighborhood I lived in London, there were a number of Victorian cemeteries that had just literally been left to ruin. Right, so they were overgrown. Nobody looked after them. People had paid for their plots. People were buried there. They had headstones, and then basically they were full, and then they were abandoned. And the reason why they were abandoned was because nobody thought that the price of the plot should include a price for perpetual upkeep. Right, so where the cemeteries were run by the church or something like that, where there was an institution that had a commitment to being around for more than a few decades, those graveyards, and a lot of them in London, very pretty, lots of famous dead people there. They look very nice, but then all over London there are these private graveyards that were set up in the Victorian era that just never had a viable financial plan, and they've all been abandoned. And now there's people, developers just look at them with a but you can't just like bulldoze the cemetery. I mean, here you can, as long as they're African Americans. But it's those are tricky things, and then that kind of perpetual the permanence of storage, that's really hard, and it isn't built into any of our structures, right? So people say, "Oh, share your code." Well, code is very small, right? But share your data. No, now it's petabytes and petabytes and petabytes, and people have looked at the size of the big data sets that people use. So CERN has an enormous data set, right? But they have an enormous facility in which they keep that data. Google has an enormous data set, but that's a commercial company that has replicated that over many places around the world, and it's relatively secure. But the scientific data, literally, it sits in like 2 places, and there's no real funding for it to continue, and nobody really knows what to do.
Yeah. And so then, Scott, we don't have gigantic refrigerators plugged into a wall for perpetuity. So how do we deal with the paleoclimatology specimens and maintaining them and making sure they stay around?
Oh, we do have big refrigerators plugged in all the time.
Freezers, not just refrigerators.
Yeah, and when the power goes out, that's
when
a moment of panic for the people that run those facilities. And it's a different kind of problem. Like the paleoclimate samples are messy. They're mud or wood or ice, and so I don't know. I think one of the strange things about paleoclimatology is focused on the past, but the people that do the work are also excited about new things. Everyone likes to go out and collect new samples, go to new places that haven't been sampled before, bring back new specimens, produce new records. That's glamorous. That gets people's attention, and that's how people advance their career in a lot of ways, by producing new records. But you have to put them somewhere. And so when new records come in, that's okay for a while, but then our shelves get filled up, the freezers get filled up, and if you want to bring in new specimens, you have to make decisions about what you have and what can go. And so there are a few places in the U.S. where there are long-term storage facilities that are intended to archive things. And actually on campus, we have one of them in the geology department that's dedicated to preserving lake sediment cores from Minnesota and all around the U.S. and all around the world. If you're a researcher, you come here to study mud that people have collected recently or in the past. But they have finite space in their warehouses. And in a lot of cases, when people retire, when university researchers retire, They have kind of like a garage sale where scientists will contact their former students and say, Alan, will you come over and take what you want for your own class so that you can leave it, because I have to retire and the university's giving me a month to clean out all my specimens, and they're irreplaceable, and some of these forests are gone, some of the ice is gone again, but I have to move them out because I don't have room in my basement for them.
And the amount of data that has been recorded by researchers that is sitting in their cabinets, that has never been archived properly, that has never been digitized, that is known to nobody apart from the people that took it, is absolutely staggering. I would estimate that far more data exists in people's cabinets than has ever been digitized and made available for anybody else to use.
Sure.
And a lot of that, like there's been the explosion in climate and paleoclimate kind of started in the 60s and 70s, big expansion in the number of people doing this. And a lot of those pioneers are now, passing or retiring, and things are getting lost. And so there's kind of this data rescue effort really has to also be something that the institutions should be focusing on, because a lot of that is replicable data, replication of data that was somewhere else, right? But has just never seen the light of day because, it takes too long to publish a thing. It wasn't that interesting. It wasn't that different. But like often in retrospect, it's the things that weren't that different that allow you to say, this is a robust result, but might not be very exciting for people to be publishing. We got the same result as we got in that paper last year.
Right. Yeah.
And it's something institutions struggle with because they don't have unlimited floor space and storage space. And if they hire a new person who's going to do a different kind of research, that person also needs lab facilities and storage facilities. And so there's real pressure to clean house and not keep these things around past the lifespan of an individual career or a research group.
Right. I mean, I think that made sense when these were being done as academic exercises, right? But climate is no longer an academic exercise, right? It's a real thing with real consequences and real decisions that are being made by people all around the world. It's no longer an academic exercise, and so things that kind of were okay when it was, this is just a class, we'll go and do this and we'll go and do this, and that doesn't cut it anymore when you're taking unique data that might actually be really important for robustly demonstrating that something is going on or contradicting it.
So those are the challenges. If you could bend the ear of those who had resources and they would listen and act, what are one or two things you think are urgent that we need to be doing as soon as possible to address some of these things in maybe ways that they're not being addressed right now, whether it's with respect to data or particular kinds of institutional preservation protocols?
Well, I mean, I'll start from the NASA perspective. So NASA has gone all in on this, and so this year has been declared the year of open science at TOPS, and as part of that, they are making more institutional resources available for these things. They're helping people. So we're helping people change the rules on what can be released, how it can be released, software, and storage, and then training people. Right, because it turns out that people who have, spent their entire careers kind of hoarding their data and hoarding their code are not suddenly, everybody says open science is the greatest thing in the world. They don't suddenly flip on a dime and say, and it turns out that how you work is different if you're working thinking that this is going to be open science. And getting people to switch, helping people to see the reason to switch. Those are things that are worth investment from all of the agencies and even the foundations, right, and the universities. So I think like kind of instituting that mindset into how do we do open science in a sustainable way And that requires everybody to be on board and everybody to understand why it is that we're doing what we're doing. That's a very important thing. So there's an educational component there. Plus, there has to be resources to help people, share code, share data, share samples.
So there's a culture change that is needed, and that culture change will require both the education and the resources to make it happen. Because if you don't, then it won't.
Exactly. Yeah.
Scott?
Yeah, I guess I would say it has to be a community effort because individual researchers by themselves can't create archives for entire communities.
Yeah.
And so it's really fortunate that, for example, Minnesota has had a big effort over 20 years to establish this university as the place where lake sediments go, not to die, but to be preserved and to be available for other people. And so you get much more value out of that initial investment. It's not just used for one study, but it lives a much longer lifespan. And I think that only happens when communities can get together and say that it's important for everyone and that they essentially pool resources and make it a priority to create centers where they can have archiving as a key element.
Yeah.
Because if you leave it to individuals, some people think it's important, some people don't. Some people are in a situation where they can cobble together some resources or pass it on to a younger person to keep the work going. It becomes much more ad hoc and inconsistent because of that. So I think the successes, where it's been a success, it's where communities have gotten together to identify particular places that are the contact point, the collection point for archives that otherwise are going to be lost.
Yeah.
So before we open up the conversation to questions from the audience, I want to invite both of you to sort of give us maybe a summary or slogan or the sorts of things that if you think the one or two things to take away and kind of keep as the item before your mind after our conversation tonight, what would those things be? The things that you would want sort of on the bumper stickers of our mind that we would be sort of circling back to and thinking about issues of reproducibility in the context of climate science.
Let's see. In climate science, what do I think? So I was a university professor 6 months ago, and then I quit to take a job in industry. And one of the reasons why I quit is because there's an explosion right now in a lot of businesses using information about climate change, climate risks now, and climate risks in the future to make decisions about their investments or how they're going to protect their investments going forward. And that's a new situation for me, and it's something I've had the chance to learn a lot about in half a year. I think it's interesting to be in an environment where no one is arguing about whether or not climate change is happening. No one is arguing whether or not it's us. No one is arguing whether climate models are useful. There's some discussions about which climate models are better, which ones are more reliable, which ones are best for certain purposes. But there's a big contrast in the way that the business is talking about climate change internally compared to the public discussions that I know people like Gavin have been involved with a lot over the last little while.
Right.
And so I think that's exciting in some ways. It's also depressing because it means that for a lot of us who are excluded from those circles, we're still stuck in the same conversations. I don't know, climate science has changed a lot for me over the period. And I think I met Gavin maybe 12 years ago. And a lot has changed over even that time. When I was a student, climate change was something that could happen in the future.
Yeah.
And then when I was a graduate student, it was something that was going to happen in specific ways. There was going to be water shortages in the American West. People were talking about that 15 years ago, and now it's coming true. And that's a eerie and strange thing to deal with. And I imagine you have feelings about that too. It's strange to make predictions and then watch them come true, especially when those predictions are negative.
Right.
And I think one of the unique things about reproducibility in climate science, climate projections is that in some ways it's a success for us when all the models say the same thing about the future. But it would be really nice if that doesn't happen. It would be really nice if all the models failed and that we don't go on that upward arc towards a warmer world. It's strange to be in a discipline where you hope your predictions don't come true.
Yeah, I mean, it's a real issue because as a scientist, right? What's your goal, right? It's to wrestle information from the universe, encapsulate it in some theory, make a prediction that comes true, and you're supposed to be yay scientist, me, ego, right? You're supposed to love that, and yet at the same time you're a citizen. And you're a person, you're a human, you're a parent, and you make predictions and they come true and you don't want them to come true, right? I make predictions and have made predictions for many years now, and I take some pride in being able to make accurate predictions, but I take no joy in being able to make accurate predictions. And so the key thing, so to wrap this up with the main theme here, is if I was just Joe Schmo making predictions and like holding up a sign in the middle of the street, you wouldn't pay any attention to me, and rightly so, right? And so robustness of the results, reproducibility of the results, replication of the results with many different methods, different approaches, models and data and observations and all these kinds of things. That is what makes this topic salient, right? It isn't an academic exercise. Right, the changes that we've seen, about 2 degrees Fahrenheit warming since the 19th century, are having impacts on your weather right here, right now, literally, right? And 10 years ago, 20 years ago, that wasn't the case. It was like it'll be in the future. But like now, this year, last year, next year, we are seeing things that are totally impossible, that would never have happened in the climate of the 20th century. Right? We are moving into a new era. And if we do not have trust, if we do not have trustworthiness in the predictions that we have, we can't possibly make decisions that are going to help us in the future. We have to have trustworthy science so that the decisions that we're making are as good as they can possibly be. And those are not the decisions that we're generally making now. We have to change those decisions. And that won't happen, that can't happen unless the science is trustworthy, and reproducibility and replicability and all of the other things that we've been talking about are absolutely essential to making that work.
Okay, I think that's a great moment of transition here to give our audience an opportunity to ask questions of our panelists. So you can ask questions in one of two ways. If you had an index card, you wanted to write something on it, I'm happy to read that out for you, but I'm also going to get up and wander. So and if people have a question, you raise your hand and a mic will come to you, and we can get your question asked. So if you have a index card, I'll collect them at the end here.
There's a hand there.
Is there a hand?
A couple of hands.
Yeah. Can we get a mic?
Hi, thanks for the discussion. Sorry. I have many questions, but I'll start with one. Are there any other natural labs which can be relied upon for reproducible results, like Antarctica and unlike Greenland, as you started with, Gavin?
Right. Well, I mean, there's lots. I mean, the ocean sediment group of folks who work in paleoclimate, who worked with the ocean drilling programs, like their big discovery in the 1970s was that if you look at the isotopes of little small forams and the calcium carbonate in their shells, it's the same everywhere you look. It's the same in the North Atlantic and in the South Pacific and in the Indian Ocean and in the Red Sea and in the Mediterranean. It's the same everywhere you look. And it's the same, it turns out, because it's a record of the ice sheets building up and going away and building up and going away, many thousands, many times over the over the last couple of million years, and that was there's really a story of reproducibility, and people have been kind of searching after that same holy grail ever since, really.
Yeah. I don't know. You can get us talking. There's so many interesting things, I think. I mean, I don't do it anymore, but being able to look into the past and see how things are connected in ways that we wouldn't expect unless we would see the signs in nature.
Right.
So just to give you a really quick example, if you go anywhere around the world and you find an old tree that's been living for 1,500 years or more, if you find rings that were grown in the year 774, a long time, 775, 776, and you don't look at the way it appears, you don't look at the physical characteristics, but you look at the chemistry, and you measure the radiocarbon, the radioactive isotope of carbon. In every tree on the planet, it goes 773, 70, 74, and then up 77, 775, it goes up, and then 70, 75, it goes 70, 76, it goes down again. And the reason why it does that is because in the year 774, there was a massive solar flare that was so strong that it knocked the global climate, the global carbon cycle out of whack for a year. And you can see that fingerprint in every tree around the planet. And that's something that it's totally outside of our experience. It's something we would never predict, but because someone measured it and it's been replicated over and over again, it provides this wonderful insight into something that we would never imagine otherwise. And so I think between the two of us, we could probably throw a bunch of unusual observations that people have made from natural history that have told us a lot about the dynamic and changing world that we live in.
All right, so I've got a question here. It's a request for comment. Please comment on the tension between the importance of archiving the immense volume of evidence and the extreme demand of energy and resources to do so. This is a question of sustainability.
Yeah, so that's a good question. How does archiving climate model output compare to Bitcoin?
Oh yeah, nowhere. No, it's nowhere. So archiving is not that energy intensive. Doing all the calculations is quite energy intensive. So people are moving their supercomputers into cool climates so that they don't have to deal with the excess heat so much. Wyoming is where they're building the latest NSF computer. So the calculations. That is a big energy issue, but compared to what's being used for Bitcoin, I read I think yesterday that 20% of Texas electricity is being used to mine Bitcoin, right? That's a whole nother level above anything that we're talking about here.
Yeah, I guess for the paleoclimate side, I think it's really modest. I mean, I know there's a similar repository for tree ring specimens in Tucson at the University of Arizona. Mm-hmm. I think there's 2 people that work there, maybe 3. There's a nice core. It's smaller than you'd think.
Yeah, there's a nice core repository at OSU in Columbus, Ohio. They have to keep that pretty cold. And there are similar. There's another one at Krell, which is in New Hampshire, which probably has slightly less problems keeping things cold. But yeah, they aren't so many and so large that they in them of themselves are a problem.
All right. Did anybody have a hand? Yeah. Okay. We'll come here.
I was wondering if you could speak a little bit to how scientists come up with the criteria for which samples they preserve and which samples they allow to kind of dissipate, given the finite resources and also given how I think you put it nicely, where when they're academic exercises, we're not as concerned about preserving them, but maybe we're bad at predicting what's going to be an academic exercise and what is going to be invaluable in the future.
Right.
So I wonder if you could speak a little bit to that. What types of discussions go into preserving of samples?
We don't talk about it. It's more of it's ad hoc. I mean, it's something that people have to wrestle with at the end of their careers or when they leave an institution. Generally, there's not really any guidelines about how to do it or what kind of choices to make. So it ends up being part of it is emotional. You're connected to certain specimens that required a lot of effort or were interesting. Part of it is broader scientific importance. So, for example, the tree ring library in Tucson will take outside specimens, but only if they think they're important. They won't take everything, and so they make some judgments that might be different than mine or someone else's about what they take in. The LACCOR, I'm not sure. I off the top of my head, I'd have to. I run into one of the LACCOR directors every morning when we drop our kids off at preschool. I'll have to ask her what criteria they use, but it tends to be kind of ad hoc and last minute, because usually when most people want to hold on to their specimens until they're forced to get rid of them, and then they have to do it in a hurry.
Yeah, I like for model data or for analyses, you think they have a shorter shelf life, right? Because next year's computer model will be better than this year's computer model. So why would I bother to keep the old one around? But it turns out that we need to keep the old ones around because we need to check how well they did, right? So, we put together a paper a couple of years ago where we tried to find all of the old climate model predictions going back from the 1960s and kind of plot them out and see how well they did. And overall, they did quite well. But actually tracking down the data, right? Like a lot of them, we had to digitize it from the graphs in the magazine, right? That's not okay. But it turns out that a lot of the other stuff just got lost, right? Like nobody thought that it was going to be important. For that model that was run in 1984, right? There's like 3 diagnostics that remain from that model. And you could say, okay, well, let's rerun that model. But then that model was before we got good at making sure that things are reproducible, right? And so, the computer that was run on, that was dismantled for scrap 30 years ago, right? Like the libraries don't exist anymore. The punch cards, right? the program was on.
They're banned now.
Yeah, I mean, I have a photograph of them, but they don't exist anymore, So we're not very good at predicting what's going to be important. And so when we go back and we find, somebody kept something, and that would be useful. We're trying to do a little bit of a better job, but we have, historically, we have not done a very good job on that.
All right. Did we have a hand here? Yeah. Microphone behind you.
Hey, thanks. I wanted to hear a bit more about the kind of division of labor between the big climate models. So
we do all the work and everybody else just.
Well, I should say, Gavin. I was in the session at PSA that Elisa put together on
world
democracy and hot models and stuff. So that's all in the back of my mind, and you'll have to explain what that means if you want to answer that directly. But I mean, just 50 modeling groups running these models on supercomputers just intuitively seems like a lot. And I get they have different heritages and mostly different code, but I want to know a little bit more about sort of the rationale insofar as there is one for having all that.
Yeah, so that's a very good question. So the event that was being alluded to was a philosophy of science conference in Pittsburgh not so long ago, and it turns out that climate kind of touches a lot of really interesting issues in the philosophy of science, and so maybe that will be something to discuss after we're done here. But the rationale, the history and the rationale are kind of entwined for why we have so many models. Is because, we started off, there was 2 models, right? But they gave different answers, and the assessment of the day said, well, so one of them is going to warm 2 degrees, one of them is going to warm 4 degrees. So let's just say it's 3 degrees plus or minus 1.5, right? That was the rationale. And as we did more models and we made them better and we added more things and we included carbon cycles and this and that, that never changed. It never came to the point where all the models suddenly came to exactly the same answer. They always had a structural uncertainty associated with them. And then as we got better at evaluating those models and comparing them to different kinds of data sets, temperature and radiation and clouds and ozone and rainfall, what we found was that there was no one model that was the best at everything. And it turned out that all of the random things that go into building a model, all the assumptions that are different in different models or sometimes the same in all the models, all of those things give you real structural uncertainty. They're telling us about the known unknowns. They're telling us about the things that we know that we don't know. And it turns out that that is very, very important to making credible predictions, because if you just went with one of the models, then you're kind of building in an assumption that you do know what that unknown is, but you don't. And so you're being overconfident. And so the reason why we've ended up with this like plethora of models is because we're trying very hard not to be overconfident in what we're saying. And so when we are confident in what we're saying, it's because all of the models are doing the same thing. It's not in the spread or in the noise of that uncertainty.
Okay, so I've got a couple questions here submitted on cards. How do you think that data-driven models like the ones emerging from machine learning techniques could affect reproducibility in climate science?
You go first.
Okay.
You go first on that one.
So the machine learning in climate science is something I'm spending an enormous amount of time on right now, and trying to find approaches that are tractable and useful. So the basic idea with machine learning for people who haven't been paying attention to this is that if you have an enormous amount of data, you can get a computer program to learn how these things are connected, and then when you ask it something, it will reproduce those connections. And so the key things that you need to have is an enormous amount of training data set, right? So the large language models that have been in the news recently, ChatGPT and things, what they have done is they have learnt all of the things that have ever been written and that are online. And a lot of that is computer code and things like that. So they're very good at making computer code, but they're not very good at doing literature searches or something like that. But they use a lot of training data and then make inferences. So the problem with that in climate is that we don't have that level of data for climate. We have that level of data for weather. And so there are some very impressive machine-learned weather forecasts that go much faster than an actual weather forecast model would go. And that's very exciting stuff. I don't think that it has any particular issue with reproducibility. It turns out that the weather generated by the machine learning is not chaotic in the same way that weather generated by a weather model is, which is interesting. And it's not clear to me what that means, but it does mean that if you run it over and over and over and over and over again, you get basically the same picture. But in terms of climate for climate science, I mean, I think there are use cases for machine learning to improve our usability of climate projections, and there the reproducibility and replicability issues will come in with, well, if I use this machine learning technique, I get this result, but if I use that machine learning technique, I get a different result. And so there we're going to have that same issue with, are there structural uncertainties that these machine learning effectively regressions are or not capturing. And so we'll have those same conversations once we have multiple versions of that. But I think you can look forward to seeing quite high profile machine learned climate projections based on the climate projections we've already done relatively quickly. And it's unclear how people will use those.
Yeah, I guess I would say, and maybe this is something we can talk about later. I am not a climate modeler, so I don't have experience in building climate models. I do have experience complaining about climate models and pointing out the things that they don't do well, or the things that they don't do that seems to be match our understanding of the way things really work.
Right.
And so for a long time, and maybe this has been fixed in the latest generation of models, but I'm not sure.
Probably not.
Models don't reproduce things like the El Nino Southern Oscillation in exactly the same way that reality does. Sometimes you see in models the tropical Pacific it swings like a pendulum back and forth between the cold mode and the hot mode, El Nino and La Nina, and that's not realistic. That doesn't match what we know from history or from proxies. And so for a lot of the machine learning applications, I would be interested to know whether they could fix some of the biases or problems in models. And I guess I would feel more interested in their application if I could see or learn about some successes that they have in correcting some things that we know models get sort of right, but also sort of wrong.
Yeah, I mean, you could imagine, machine learning to do downscaling of climate model projections to local data, right, to local stations, where you have a link between all the different things that are going on in the climate model, all the different things that are going on in the real world, and then you can kind of learn from that and produce downscale data. So I think you're going to see that. I think you're going to see some success, though not as much as people have predicted, in replacing physical parameterizations in these models with data learnt parameterizations that would be perhaps built on remote sensing data or something. But that has not been as productive as people, I think, thought it was going to be 5 years ago.
All right. Here's one. What was the temperature of the Ice Age? Did they even determine this? And if so, how?
So that's a question.
It's a good question
of,
for a PhD comprehensive exam.
Yeah. And it's an area of active research, as they say. So there are temperature proxies that can be dated to the last ice age on land. There are snow lines, there are moraines. You can see where the ice got to. You don't quite know how thick it was, though you can infer that from how much the isostatic rebound is changing in the lithosphere. We have isotope records from the ice sheet regions. We have oxygen 18 alkanone records in the oceans, but we still have gaps. And so if you do a kind of raw average of the change, you end up with something between, what would it be, about 8 to 9 degrees Fahrenheit colder than the pre-industrial at the last ice age, the peak of the last ice age. And then people are doing like kind of more sophisticated data assimilation efforts where you take models of the last ice age and then you kind of fit them to the data in some relatively clever way. And that gives you a slightly cooler ice age around, maybe 10 to 11 degrees Fahrenheit colder. So it's still, it's not 2 degrees colder and it's not 100 degrees colder. It's around somewhere between 8 and 10 degrees Fahrenheit colder. And that's one of the targets that we now use to evaluate whether climate models are in the right ballpark for what's going to happen in the future. Is can they get that temperature right in the past?
Okay, so next question. Is climate change itself changing the reproducibility of climate science? For example, changing model parameters that are assumed, forests burning old trees. If so, how are scientists in the related fields coping with that?
So that is a good question, because there are a lot of people that use climate data in some way that are often based on historical data, right? So people who are looking at water resources, they have rules of thumb that relate, the snow depth in this particular field in the Sierras to water resources availability in the spring following, right? Or you have degree degree melting days for assessing the health of a glacier and the like. And a lot of those things are based on statistical correlations that were developed in the 20th century. And now things are not stationary anymore. Things are moving. And so it isn't clear that a lot of those statistical correlations will still hold up in this new situation. You may end up, I mentioned Texas again, right? So the Texas grid assumes that once the temperature goes above a certain degree, they think that all of the air conditioning is on, and therefore they don't need to build any more capacity because it's going to peak, right? But it turns out that was only a kind of statistical artifact from what people had in the 20th century in terms of air conditioning, and now that's no longer true. And so their forecasts of peak energy use in the hottest days or the coldest days are just fail abysmally, and that's causing real problems. So yes, I mean we have embedded information about the climate in many decisions that we're making, and those embedded assumptions are no longer as stable as they were, and so that is a problem. Yes.
Yeah. So the question is modern climate change making understanding climate history more difficult? Yeah, that's certainly true for anything based on ice, because every system connected to any mountain glacier anywhere is getting smaller. It's smaller than it was even 20 or 30 years ago. Yeah. And so when Gavin mentioned some of these tropical records that people have obtained, some cases of those ice sheets, the glaciers aren't there anymore, so you can't go back again. You can't resample them. I think for other kinds of climate history, change is not so much the threat as just human activities. We're very busy, and we're in most places all the time harvesting forests and changing watersheds, and so just the act of being.
Yeah, I mean, finding a pristine watershed that doesn't
really exist anymore. Yeah. And so those places, those forests, are not necessarily being harmed by climate change, not yet anyway. But it's always a race against time, because people are busy and people are everywhere, and so it becomes harder and harder to look back into the past as we go farther into the future.
Okay, so one last question, and I think this one is a good one for us to close with. If this work is no longer an academic exercise, how can we change the material conditions of being an academic to foster reproducibility and replication? Why do people doing this work have to fight tooth and nail for funding? How can reproduction of results be incentivized?
It's a great question. I don't know the answer.
I don't know. I guess I repeat something that we were talking about before. So I left academia half a year ago and worked with industry, and in my industry, which uses information about climate to make decisions or to help people make decisions about climate and weather related risks, we depend on public science enormously. We depend on the model simulations that Gavin and his group and the other groups do. We depend on public information collected by agencies like the State Climatology Office and other places. And so, I mean, in some ways it's a tension, right? Because those institutions are traditionally fairly modestly supported. I was always surprised when one of the main products that is associated with Gavin's office in New York is this global temperature record. Mm-hmm. And I remember a few years ago I had caused, I think, to email either you or Rudy about it, to ask some questions about how I could get a slightly different version of the data set. And there's like 2 people there.
Yeah, not even
3 people. It's 1.5 persons at NASA.
It's about a 0.25 FTE.
I mean, you imagine rooms and rooms of scientists keeping track of global temperature, and it's like one guy named Rudy. And when he retires, it's not clear if there's someone to replace him. So it's this strange tension where where those areas have traditionally been sort of a little bit obscure and sometimes political football, but at the same time they're enormously important, and a lot of people are making a lot of money off those efforts.
Yeah, and you know, and I think things may start to change. And so right now people make a lot of money off weather forecasts, right? So AccuWeather and the Weather Channel and Weather Underground, they're all private companies that provide bespoke things for the TV, for the websites, and most people are not using the direct forecasts that come from NWS or from the European weather forecast or the Met Office. They go through an intermediary, and that's totally fine, right? And the federal government is very happy. Rather strangely so, but anyway, it's very happy when people make money off the government efforts. So as I think people start to invest more in the private sector response to climate, I think that becomes an incentive for the federal government to invest more, so that what is being provided is A, being provided fairly, and B, is of some quality that can be assured. And I see that happening. I was involved in a lot of interagency things, last year, and it's a slow thing to shift the interagency business. But the current administration is very pro these things, and so it may happen that there is a step change in investment in both. Data accessibility, the ability to test whether things are reproducible, but then also the usability of data. And I think that there are serious efforts underway to make that happen, but it isn't. There's a ways to go.
All right. Well, we are at the end of our time, and I want you to join with me in thanking both of our panelists for sharing this evening with us. They will be here for a few minutes as we clean up if you'd like to ask them another question. And we will be sending out a email with a link if you would like to provide us with any feedback on the event. We would appreciate it as we plan future engagements. We appreciate you taking the time to be here with us tonight, and look forward to seeing you again soon. Thank you. Take care.
Thank you.
Thank you.